और सब मतलब कैसी है? ठीक ठाक है। अभी अगर आपसे कंक्रीट की बात करें ना, मार्केट की मटेरियल जो कंक्रीट की बात है, ये इसके डिजाइन एस्पेक्ट स्ट्रेंथ और वो पैरामीटर्स एक अलग पार्ट है। इसकी जो वही जो आप कार्बन फुटप्रिंट की बात करेंगे वो एक अलग सेटअप है। अब इनके लिए अलग अलग टूल यूज करते हैं। तो आप जब वो मेरे पास मैं जो बहुत सारे सॉफ्टवेयर का आपको लिंक दिखाता हूँ, उसमें टॉप में एनर्जी प्लस जो है वो बिल्डिंग के एनर्जी जो हीटिंग कूलिंग में, लाइटिंग में, वेंटिलेशन में इस्तेमाल होती है। और इसमें जो एनवेलप के पैरामीटर्स हैं जिसमें मटेरियल की सिलेक्शन आती है वो उसको कवर करता है। अब जो वो मेरे ख्याल में एशिया के जो बोर्ड है रेफ्रिजरेशन से रिलेटेड जो हीटिंग रेफ्रिजरेशन ये ज़्यादातर उसको फॉलो करता है। लेकिन इसमें प्रोविजंस हैं मटेरियल की सिलेक्शन की, स्ट्रेंथ पैरामीटर्स नहीं है।
लेकिन उससे ज़्यादा
बिल्कुल मल्टीपल चीजें मतलब आपको चीज देखना है। देखिए अब आप जो आपने डायरेक्टली ये बोला कि मैंने 40 को भी करना है और 60 को भी, तो आप इसमें आपको सॉफ्टवेयर जुड़ेंगे जो IFC के साथ सामने रखते हुए ये 40, 50 और 60 को कवर करता है। और ये वो ऑलरेडी ये पूरी लाइफ ऑफ द स्ट्रक्चर की सिमुलेशन जो आपके बेन रेलेवेंट सॉफ्टवेयर पूरी जो IFC जो आप इधर करेगा इसमें डाला और एनर्जी साइड पे एनवायरमेंटल साइड पे क्या था और दूसरी जो स्ट्रेस वर्सेस कुछ कवर
और इंडस्ट्री बिल्डिंग से इंडस्ट्री होती है जो प्रिपेयर करती है उसकी अपनी मिस्टेक को अपने उसके बाद उनको प्रिपेयर करती है फिर आप एनवायरनमेंट की बात करते हैं एनवायरनमेंट से
फैब्रिकेशन की बात करें या फिर इवन आपके जो कंट्री वो भी बन रहे हैं फैक्ट्री में तो वो रिसाइकलिंग का प्रोसेस है उसकी स्क्रीनिंग करनी है वॉशिंग करनी है वो
मिक्सिंग वाले लोग जाते हैं फिर हमें जो है इस तरीके से रिप्लेसिंग वाला है कंप्लीट इंडस्ट्री में कंप्लीट बिल्डिंग्स इंडस्ट्री उसके बाद ऑनर बिल्डिंग अपनी कंपनी को या अपनी बिल्डिंग में स्टे करना
ये भी इसमें कवर हो जाएगा आप एक सॉफ्टवेयर नाम रखें ये अभी मैं इसका करंटली फ्री लाइसेंस भी मिल रहा है स्टूडेंट्स के लिए 3D ये 3D experience by Assault Cinema
yes
3D experience और इनका ही एक और सॉफ्टवेयर लेकिन भी अलग नोट कर लीजिए सुना होगा ये जो आपने जितनी बातें की हैं इनके कनेक्टेड ये सारे टूल्स इवन जो आपने ओनर वाली बात की थी ओनर के डिमांड उसके साथ उसको कैसे करेंगे उसकी क्या रिक्वायरमेंट है वो सब चीज़ें उसमें कवर
हमने घर बनाया इसकी फाउंडेशन बनाई किसी कंक्रीट से तो कोई आर्किटेक्ट को था ही से वेरी सस्टेनेबल वो के बनाया उसके बाद फिर आगे भी मैं कुछ स्टेबल ऐसा काम करूँ जो मैं उसको लाइफ अपनी लाइफ में कर जाऊँ तो ये उसका प्लान था राइट उसकी फाउंडेशन से बनेगी और मैं यहाँ पे बिलिंग नहीं होती न्यू मटेरियल है हम तो यूज़ करेंगे तो कैसे चलता है कि इंश्योरेंस कंपनीज पर आ जाते हैं ऊपर कहते हैं कि न्यू मटेरियल है हम आपको इंश्योरेंस आ रहा है तो देखिए आपको कवर नहीं स्टेज होती है
टूल्स वन की ऑलरेडी आईएसओ स्टैंडर्ड में आप आ चुके हैं ये भी नंबर एक साल भी उसको सो अभी जब आप एक ऐसी आर्टिस्ट के सामने कहेंगे कि ये दिखाएं सर्टिफाइड लेवल की किया दे हैव और वो तो अभी मतलब ये प्रोफेशनल
जो है उसको फोकस करने के लिए ये जो मिलता है ये सॉफ्टवेयर है ये काम ये मेरे स्टेक होल्डर्स हैं इन्वॉल्व होते हैं फिर मुझे फाइनली स्टीकर मैनेजमेंट
सॉफ्टवेयर बहुत सारे
ये कुछ कनेक्शन है उसमें
That's okay. Many other people wouldn't find it.
I mean, sometimes आपको try करना अगर आपको फ्री नहीं मैं ऐसी assignment.
So, what is your plan for today? Like after this? I want to see the lab system. Oh yeah. After we see the lab, like I was thinking, do you have any preference for the my wife is actually that she can use obviously we have and we can all cook. I also ask my family to join. We can go to like kind of seafood. So we'll go to Tokyo restaurant. Maybe right after we see the land, we can. After there, we can go for a walk in the lakeside. Yes.
Yeah, that's fine. Yeah. Okay. So I'm planning to finish around 5:50, and it will be around this. Okay. So let's move on to our next analysis topic, which is pushover. It's all right. I project well, so I don't even notice. Who here has done Toastmasters by any chance? Anybody?
Toastmaster. Oh,
Join.
do you know Toastmaster? No.
Join, it'll help you with public speaking. Okay, so we'll talk about pushover analysis. This talk, just an overview here. What does it mean and what's the need? Basically an illustration describing the concept. Moment curvature analysis, as I was saying earlier, it's an input into the pushover analysis. Most of your lives, you'll do automated pushover analysis. You'll make some inputs into the computer, it'll run it for you, you'll get some results. You'll have to make sure that the results make sense, obviously, and you'll move on with life. But a lot of people don't understand what is happening in that black box. What is a pushover analysis? What is the computer doing inside that black box? When I joined my second firm, my boss that I have a lot of regard for and a lot of respect for, he made me do the pushover analysis using the linear software because he wanted me to understand what's physically going on. So in this talk, I want to run through the steps that you can use to run a pushover analysis if you have a linear software. Or you can do a one-step pushover by hand. It's imperative to my mind because it really makes you understand the underlying philosophy, the underlying concept. And I'll talk a little bit about the Manders model for confined concrete. I'm sure a lot of you are already aware of that. So where does and how does the need arise for a pushover analysis? It's basically used to determine the displacement capacity of bridges. So think of this as less of a demand tool and more of a capacity tool, even though out of it comes several demands that we use. But it's a capacity envelope that you can come up with while figuring out the nonlinear events that happen in the life of a bend as it is being pushed farther and farther. Okay, and this is our basic analysis tool to verify our design adequacy for performance-based design. You cannot do performance-based design without a pushover. You could just run a nonlinear time history analysis and get your results. I would strongly advise against that. You always go, in my mind, from simpler analysis to more complex analysis. If you were to run a nonlinear time history analysis, you wouldn't have a clue unless, I guess I still don't, maybe you have 50 years of experience and then you already know where the nonlinearities are going to occur, what kind of behavior, how the load path is going to change as nonlinearities kick in, maybe. But we always go from simpler analysis to more complex analysis. And when it comes to capturing nonlinearities, a pushover is an advanced enough tool, yet simple enough to help you get the grasp, the understanding of how the structure is going to behave. It also helps you identify the plastic hinge sequence and also lets you capture the resulting plastic demands or quantify the plasticity in your structural fuses, so to speak. You can also look at the intermediate damage states because you can come up with your plastic rotations or curvatures and material strains in your ductile substructure elements. We can also use it to determine the degraded shear capacities as your local ductilities are increasing, because the formulations we've got right now are all tied to the ductility demand levels. So if your curvature ductility is this much, there have been some studies done that say you should reduce your concrete capacity by this much. If you haven't run a pushover analysis, you won't know how much local ductility you're sitting at. It's very difficult to figure out what degraded shear capacity you need to use. Again, we can quantify the post-elastic capacities and component integrity, such as for aftershocks. And I'll show you a little diagram that I came up with, and people have looked at it and said, given that there's nothing else available, this is not a bad starting point, at least give it a first thought. We can also look at the deficiencies in detailing using this. It's not directly, it doesn't directly give you that info, but it kind of tells you where the issues are so you can go and probe a little bit deeper. It starts to give you a picture of where the damage is occurring and how bad it is. And then you can supplement it with other things, and this will become a bit more clear. Right now I'm just setting the stage to see what is going to happen. Again, or in addition, we can calculate the overstrength force demands to basically stop or circumvent our non-ductile failure modes from kicking in. Okay, so footings being column joints, column footing joints, cap beams, shear in all of those elements. Those are things that we want to avoid, and we want to design those against overstrength demands, not your base design demands. As I said, that under prediction can really kill you. So it helps us with all of that. Okay, so here is, I'll just explain what's on the previous pages, but a picture is worth 1,000 words. So this is again a simple, very simple cartoon, 5 girders, their dead load is sitting on there, and you're gonna come and you're gonna push it with a displacement or a force. Let's say the displacement compatible force is B. The potential plastic hinges that can form are at the ends of the beams and the ends of the column. So those are those 6 dots. So what do? First, we load it with the gravity loading. So this is an analysis which, unlike the response spectrum analysis, is started from a stressed gravity state, because there is already an axial load in each column. There are bending moments and shears in your columns and your cap beam. Those are locked in already. If you think back to the very first cartoon I showed you with the bending moment diagrams, you know that that load is already there. And when you start to push on it, now that state starts to change. So we can't just start pushing on it without accounting for gravity.
So
Yes.
you're showing already the positive bending moment in the middle there.
Yes.
So
Here.
is there no possibility of plastic information in this location?
Unlikely, because what happens is, as it goes into this, as you can see, it starts to reverse it. Okay, so the bending moment in the middle of the beam starts to diminish. It increases as positive on the one side and negative on the other side.
So you're saying that in the load figure, the bending moment diagram on the beam is because of both the lateral force as well as the
No,
girders?
this is just lateral force itself.
So then you're
So then-
ignoring the girders are gone?
No, the girders are still there, but this beam has been designed for gravity load for sure, right? That's sitting there.
But in the seismic condition,
Yes.
the girders load will also be there.
Yes,
vertically.
it's still there. So now you add these two to get your final condition.
Fine.
Right.
But then again, your predicted location of plastic hinge is still you're ignoring.
Yeah,
that
because here you see it's pretty much zero.
Okay.
So add to that, you don't get too much of an increase in the middle.
This is your criteria.
Yeah, that's when you look at this, you keep pushing it, the middle is not seeing much. It's seeing a little bit of positive here and a little bit of negative here. So it might add a little bit here and a little bit there, but that's not where it's going to go. That's where the huge jumps are. The reversal is happening here, and then there's a big increase there. This column gets a lot heavier, this gets a lot lighter. So the beams, almost you never see them forming hinges here in my experience. They always form hinges at those locations. Okay, so the 1 and the 2 are superimposed. So now you have a new bending moment profile. And as you keep pushing, again staying with this picture, as you keep pushing, this negative starts to turn into more positive. This negative starts to become higher. This bending moment in the column here and here and here and here, they start to increase, right? And this side, they're reversed. This starts to decrease and this starts to decrease. They're acting opposite to each other. So at some point, you're gonna see that this moment is very small, this moment is very small. These moments are really high. Okay, so the likelihood is going to be that you're either, depending on how strong your beam is versus the column, you can either form a hinge here or here or here. Okay, so now just think that you keep increasing your lateral push, you keep increasing the force. At some value of that force, the corresponding bending moment at, let's keep it simple, at any of those 6 points is going to hit the plastic moment of that section. As you keep pushing it, one section is going to hit its capacity. And now that section has formed a plastic hinge. And a plastic hinge then has very little stiffness as compared to sections that have not formed a plastic hinge. So now this, because of the stiffness difference, there is very little moment accumulation that's going to happen within that section where you form the hinge. So you could think of it as a pin now, which has a locked-in bending moment. The bending moment that is in it when it formed the hinge hasn't gone away. Why? Because we've detailed in a ductile manner, we've made sure that the fuse doesn't allow the force beyond that level, but that it keeps operating at that level. It's not like an electrical fuse that just, boom, destroys itself, and because in that case, you just have a failure there, okay? So now you have a system. Now you have a system. I don't want you guys to get lost in the words there. You can all read that. So let's see here. And I'm going to just stay with the columns and say my beam is strong enough. Okay? So how do I capture all of this and do it with a linear software? I'll show you the CSI thing in a minute, but let's just think of it as just from a conceptual point of view. This is my force displacement curve, which is otherwise known as the pushover curve. So at some value of V1, this location forms a hinge. Now this system is moment connection, moment connection, moment connection, and a pin. Now, when I push it more, you'll see that this line, its stiffness is going to drop. It's going to become more flat because that thing has very little stiffness left. And I keep pushing now. The bending moment here cannot increase. It increases here, here, here. At some other force value now, another section is going to reach its capacity. Okay, so let's say that this is getting lighter and the next hinge forms at that point, and that's hinge number 2. That's my V2. And you keep pushing it further, you might get a third one, and you'll see more flattening of this line. So we started with 1, 2, 3. And then as you increase the force more, now this is becoming a little bit repetitive what I'm saying, another slope change. You get to V4. And if you assume that now the hinges have very little stiffness left, and maybe a little bit of post-elastic stiffness in there, this is going to be a pretty flat line. Okay? So what happens now, as you were saying in the morning, now it's unstable. So if earthquake were like gravity, and it just kept pushing it in this direction, what would happen? It is unstable. The only saving grace here is it goes this way, then it goes the other way. Back and forth, back and forth. How can the failure actually happen? So the first hinge that forms, say this one, as soon as it forms, as the forces are increasing in the other locations, it's accumulating what? Plastic deformations. So it's already going down that plastic path, and it only has so much of that available to itself. Now, different hinges will have different plastic capacities in them, which are not infinite. So this line, theoretically, you could draw it till the cows come home, but you know that somewhere something is going to give. And when we go a little bit into the moment curvature analysis, I'll talk about this. But at some point, one of the hinges is going to exhaust its plastic flexural capacity. And let's say that that's this point. That is really our failure point. This doesn't mean anything beyond that. So if your hinge has failed to the point where either your rebar has ruptured, or it's badly buckled, or your concrete core has crushed, then that local section is really just out. You don't want to keep relying on the system beyond that, because now it's doing very quickly, it'll do this. So in terms of any realistic performance, any realistic capacity, as soon as your first hinge reaches its flexural ductility, you say, that's it. What is the inherent assumption in there, given what we've talked about? that the hinge is reaching its flexural capacity. What other things have not happened so far? Has there been a shear failure prior to that? No. Because if a shear failure happened prior to that, you'd have some shear failure happening. Maybe this hinge is coming down, and by the time it hits that point, it's exhausted its shear capacity. So this means all other modes of failure have been suppressed. Then you can get to that theoretical point. Okay, this means your joints have not failed. This means your foundations have not failed. This means your cab beam has not failed. So this is the argument that you can get, given that we've suppressed everything else. Okay, now let me quickly add one thing here to bring this into context. Just a very global sort of context. Why are we doing this? So let's say that your bridge is another bridge. And for another bridge, one of your performance requirements is 2475 no collapse or life safety. I run the response spectrum analysis on my system with my appropriate effective stiffnesses or crack stiffnesses. I get my delta 2475. And my delta 2475 happens to be here. Have I met my performance level? I have, because my failure as defined for that performance level, which is life safety, which I'm saying this is the line, I don't want to push it beyond that. Oh, you test something in lab, and I was looking outside last night, I just came for a visit, I saw a couple of columns, it's just bent rebar and there's no concrete around it. That's not how far we push the system, even though it's standing, a little jolt and then it's gone, right? So we say, well, this is realistically where I stop. My response spectrum delta 2475 with cracked stiffnesses is here. It's before this point. And the code at this point says your equal displacement principle is valid for bridges. Just use that. So use your response spectrum elastic displacement, and we assume that that is your inelastic displacement. That matches here, I'm fine. Okay, now I have my delta 475, let's say, and it says this is corresponding to an E sub C of 0.006, and E sub S of 0.01. Okay? I'll talk about it, but I can use your strains, those strains, and rotations and the member length, etc., to come up with the displacement value. Okay? This is the capacity side of things I'm talking about. So let's say that that is just happening just about here. So my hinge is just forming. I have a little bit of plastic strain in it. Let's say that it's 0.01 and this is 0.0045. So this is hit. And that value of delta 475 is, that's my capacity, just as this was my delta 2475 capacity, and this was my demand. So this value is my capacity, and my demand, when I run the response spectrum analysis, is sitting over here. Have I met that performance level? No, because my demand is sitting beyond the point that defines my performance level. My performance level displacement here is this in blue. My demand is here in black. And this comes out of this. So this is how the pushover is going to help us figure out if we're meeting the performance. We'll go into more detail as to how we determine the capacity. The demand comes straight out of your response spectrum analysis. But I wanted to set the stage. I want you to understand how this tool is helping us. Okay? Okay, so I think we've talked about a lot of that stuff that I have on there. So let's now get a little bit deeper into this thing and think about how we can say, well, I'm sitting at 0.01 or I'm sitting at 0.006. How do we get to that point so that we can come up with actual displacements? I'll leave that there for now. We might have to come back to it. That's where the moment curvature analysis comes in. Okay. So everybody here, have we done axial moment interaction curves? So you basically put an axial load on a column, you keep increasing the moment, and at some point, you get your strain value of 0.0035 on your concrete. And you say, well, that's my capacity. If you look at the codes, AASHTO, S6, etc., from a nominal capacity point of view, that's what we do. And our P.Eng diagram kind of looks like this. Whereas this is the compression portion, this is the tension portion. And as long as you're in here, your column is okay. So this is just staying between P and M. This doesn't give you any idea of curvature, of rotation, of strain. Whereas in this code, when we're going to these specific performance levels that are tied to strain values, we can't use this. We've got to do something else. And that's where the moment curvature analysis comes in. So this is a simple thing, right? You've got a circular section or a rectangular section in this case. I'm going to put a constant P on it, and then I'm going to start to put an increasing moment on it. So the P remains the same, the moment increases. Keep that in mind. As I keep increasing the moment, the concrete is going to crack at some point. Then what's going to happen? The rebar is going to yield. Then it's going to go into strain hardening, on and on and on. At some point, my concrete is either going to crush or my steel is going to rupture. Or I can decide that I'm going to stop before then at some other strain value. So whatever my performance point is, I can do that. So if you look at the free body diagram here, you see that this compression on concrete plus the compression, this is the compression and tension. These are the compression and tension due to the bending moment. Internally, that's what the bending moment turns into, a compressive force on concrete and a tensile force on steel. And this is the external P. So the external M is this, and the P is here. So if you look at the free body diagram, you get CC plus P equals T, or P equals T minus the compression in concrete. And as you put more and more, this is where your neutral axis starts. It's your elastic neutral axis. By the time you hit a certain strain value, you've gone plastic. Your neutral axis is always moving up. Okay, just a bit of a revision of thinking back to what we used to. We've studied back in the day for everybody probably, because everybody's a graduate student or beyond. So now what happens is, you can do this analysis called the strain compatibility analysis, which is what's done here. This is your strain profile at that point. The curvature of, or the slope of the strain line is your curvature, right? It's the second derivative of displacement. So this phi, which is in radians, can be calculated as the perpendicular over the base, which is the EC over KD, or I can calculate this as epsilon S over D minus KD. So that's just taking similar triangles. So once I've put a moment, I can come up with the strains at each level. And once I've hit a certain strain, I can figure out what that moment is. I can calculate the forces, their lever arms, I can come up with the moment value. So as I keep increasing the moment, the strains keep changing, the curvature keeps increasing, the moment keeps increasing until a certain point when all the steel has yielded, and then maybe it's gone into some sort of strain hardening, but really now you're getting to the limit. And this is what I was describing earlier. This is your moment, this is your curvature, kilonewton meters or moment units, and then radians per meters over here for curvature. So MIY is your initial yielding, your cracking happens somewhere here. Now when we think of a plastic hinge, it's not just as soon as your first rebar yields. Okay, you don't quite define it like that, especially in a circular section, because you've got a circular section and the centroid of rebar is different for each bar. It's a bit more defined for a single layered concrete rectangular column, because they're all going to go at the same time. So what we do is, a lot of the softwares, they'll take the origin, they'll draw a line from the initial yielding, and they'll bring it up to some point and they'll match it to the ultimate. The ultimate depends on how we want to define it. I can say, look, because I'm going to be cycling my steel back and forth, it's going to rupture at 75% of its monotonic rupture strain. So instead of 0.09, I'm only going to take 0.06. So I can tell the program to stop as soon as my steel hits 0.06 or my concrete hits its crushing value. And you try to equalize the area under these two graphs. So here the red line is higher and here the red line is lower. And then you say that's my effective yield. So this is my initial yield curvature, that's my effective yield curvature, and this is my ultimate. And that's how you can bilinearize this with a little bit of a post-elastic slope to your hinge. Now this becomes an input into your software. Okay? The best program, to my knowledge, that I really like for moment curvature is Extract. That's a commercial software. You can also use Response 2000, which is free out of University of Toronto. Extract has a lot more versatility, I would say. It gives me a lot more in terms of, I'm not going to demonstrate this in class, but Response you can download and you can play with it. Extract is a little bit of more of a commercial thing. Okay, so now have a look at this. Here I've modeled a column with no axial load on it. Its loading name is P-0. So it's got all these finite elements. It's got the unconfined concrete properties on the outside in the cover. The core is confined with, say, stirrup, so we need to use a different model in practice a lot of the times. And I think if you look at Seismostruct or others, Mander's model is a fairly standard model that we use, which gives us a much higher strength of the concrete and also a much higher crushing strain for the core. So here it's going to tell me what's going on. So there's my moment at first yield. I know you can't read it, but just take my word for it. There is the ultimate moment. There's effective yield curvature, effective yield moment. So it's already done all of that for you. It's telling you the effective yield curvature. It's telling you the effective yield moment. It's also giving you the initial yield moment, the initial yield curvature, and then it'll give you the final curvature and the final bending moment. So I can play with this program and I can stop it right when the cover spalls, which I say is at 0.004. Or I can say to the program, let the cover spall, because that's not a big deal. I want to keep going because I know the concrete core is really well confined. So let the cover fall off, disregard it for strength and everything else and stiffness, but just keep going because I've put 15 Ms at 50 mils. I can get a lot of capacity and ductility out of my core. and I'm designing for a 24, 75-year return period event, I don't care if at a higher level it's fault. I'll just go and get a contractor mobilized, and they will put it back together as long as the core concrete is fine. And when you look at the core concrete can be relied upon. In fact, for higher levels of performance, the code assumes that the cover has fallen off, but it lets you go on. It now ties your performance to the core concrete. Now this is the same thing, I think. This is 36 cents before with 0 load, and now it's got 4,000 kilonewtons of load on it. So you see the difference here. My bending capacity is about 9,000 kilonewton meters. Here, it was about 10,000. But look at this. The ductility out here is about 0.016 for curvature, and here it's only about 0.012. So as you put more and more axial compression into a column, into something, the ductility reduces. The strength can go up, but the ductility will reduce. The strength will go up if you're beyond this point, if you're below this point. If you're beyond this point, then it starts to decrease again. What's that? So this is the original curve, the pink. Okay, so you will see the first stiffness here, and then there's a break in stiffness, which means that's where the concrete is cracking. Then it's progressively, all these dots are when your rebar, or that's where it's calculating the numbers. But your rebar is now becoming more plastic. And this is the bilinearized curve that I was talking about before. This is where you go through your first yielding and you try to equalize. So this is just in the program, when you use SAP or others, it's you don't put a very complicated curve. You simplify it as a bilinear curve. So that's the program is already giving you that. That's why it says moment at first yield, and then it says effective yield moment. So it's giving you moment at first yield, but it's giving you effective yield moment, which is a bit higher. So now you can, if you do this, you can calculate your actual effective EI. Remember, I had said that you could use the charts, but you could also use a more sophisticated method, which is this moment curvature. So in the program, it tells you that your initial yield moment is 6852, initial yield curvature is that much. If you divide the two, you get your EI effective. Now you have to calculate your EI gross to figure out what the ratio is. Is it 0.4? Is it 0.8? What is it? So IG is given by pi d4/64 for a circular section. EC is given by a code formula. So if I multiply these two, I get 31.3 times blah blah. So that ends up being about 7.78 10 to the 15. And EI effective is 2.6, which then gives me a ratio of 0.34, 0.35. So now I can go back and check if I've used 0.35, 0.36. If you use 0.32, there's no need to go back and revise it because the difference from response spectrum analysis is just not going to be there. So put yourself in that sort of frame of mind where if you're doing this 0.31, 0.32, it's not that much of a difference. Yes?
So in that case, the yielding temperature is one corresponding to the yielding of the steel, the strain rigid of the
Yes.
steel, or the idealized moment temperature?
No, this is the initial yield.
So on the strain...
Yes, that's what we use. Because that already gives, well, this idealized point also lies on the same line. And EI effective is just the slope of this line. And so it's just an extension of the same line going through that point. So if you use that point or this, any point on this line, but we only know 2 points on this line. So you can use the effective over the effective or initial over the initial because it's the same line. So you're going to get the same slope. Okay, so that gives us a 0.35 kind of thing. Now this is a different scenario where I have a steel pipe pile and I've put rebar and concrete into it. So now this steel really confines the concrete very nicely. And on a lot of the order bridges, we go and we put these steel jackets around the columns. So we bring in two sections that are a bit larger than your column, and then we weld the seams together, and then we put grout in that so that it becomes one body. But what we try to do is not anchor the bottom of the plate into the footing. So we leave a little bit of a gap. So at that location, you're trying to not bump up your moment capacity too much, right at that plastic hinge zone. So we're using the steel really to confine, to provide confinement, so the rebar, pull out the lap splices, the shear, all of that gets pumped up. But your local base bending moment capacity is not high right at that interface. But now you need to use this confined Manders model, and the program does this for you. I have a couple of numbers after. So again, you can play with the parameters, and it gives you the moment curvature values. Okay, this is really, really bad, but what I'll tell you this program will give you is for every moment value, so as you're increasing the moment, it captures so you saw the graph and those little points, it captures the moment for every point, it captures the curvature for every point, it gives you the unconfined concrete strain value for every point, both in compression and tension. It gives you the confined concrete values for compression and tension, and it also gives you the rebar values. So for every bending moment value, the corresponding curvature and all the strains are available, you can output from this program. How does that help us? I'll explain in just a minute. So this is slightly different. This is saying my P is that much, my nominal expected value is this much, and my overstrength is this much. So now think about this. The underprediction of your basic capacity in seismic design is not a good thing. So for capacity design, we want to bump up our capacities so that we can capacity protect against those higher demands, right? We've talked about that quite a bit. So the code has different codes you'll read, and they'll tell you different things. They'll say, first come up with your nominal expected capacity, which means you put 10% extra on your rebar and 25% extra on your concrete. That's just giving you your basic capacity. And then you multiply that value by a 1.4. Or they'll say, don't do that, but use a 1.3 on your concrete and a 1.7 on your steel. So bump up your concrete by 30%, bump up your steel by 70%, get your capacity, run your pushover. Now use those demands to come up with your overstrength shear and joint shear and all of that, now, and your cap beam and design for that. Whichever way you do it, you just want to make sure that when you are looking at overstrength design, that you don't use your basic values, that you're using to show these performance criteria. These performance criteria are based on your basic design values. The overstrength is based on a factor that bumps up your basic strength because you don't want to underpredict that, okay? Yeah, so now this is a composite section with steel and concrete together. And here you can see that my failing material is my concrete. Its compressive strain value is 0.02. Usually concrete failed at 0.004. When you confine it, it's a 5-time bump. And that's why you see so much ductility in it. Okay, so this is before the steel shell ruptures. But it's so much better because you've confined that concrete, and that it has no unconfined concrete anywhere. It doesn't have an unconfined, what do you call it, cover. Everything is confined within.
So it's almost the same just has
It just has the steel around it.
the strain as a phi and
Yeah, so the strain is going to be different. Over here, these are the curvatures. Okay, so this is an 1840, a 762. Strains I haven't taken out, but like the effective yield is about 3,000. And I think the previous one, this is a 1500 column. So they're not the same. No. But if you were to do an analysis on something that's 762 with and without the steel, you'll see a big, huge difference. Yeah. Now you see how this is very, very flat, like it doesn't go like that because it's rectangular. So the CG of this is all the rebars are going to yield about at the same time. Whereas a circular column, you have progressive yielding, so you get more of a ovalization of your curve. Here it's up and straight and it goes. Now if you kept it going, at some point you're gonna get your rebar going into strain hardening. I've stopped it at 0.0035. So when I set the parameters within the software, I said stop as soon as my unconfined concrete hits 0.035. So I can control that. Okay? So this is really giving you the first nominal capacity. It's not accounting for a lot of other things. Okay, so very quickly, let's look at this bent. I've got a bent with 4 girders. They're at 3 meters, and then I've got a 7200 clear length of the columns. I've got a 10.8 meters wide width cap beam, and the footing is 1.5 deep. The cap is 1.8 deep, and then I'm saying the CG of the deck is about 2215 from the top of the cap. And what I want to show you is how to do a quick pushover that's not automated. Okay. So first, what you need to do is you need to generate your moment curvature curves. Okay. That has to be done separately because that becomes a bit of an input into the system. So what I've calculated here, what I've tabulated here is for a given column, for the column that's shown over there, I've drawn the P.Eng values. I've written the P.Eng values, but the M values are the effective yield values, not the initial yield values. Because the assumption is that a hinge is reasonably assumed to form when you hit effective yield, because initial yield happens much, much earlier, and it's just the first bar that yields. You don't take that. Okay, so I've got this. And that's based on what the code says. It says for your basic design, use 25% extra on your F'(C) and 10% extra or 20% extra for your rebar. And that depends on what the R value is, but for performance-based design, we can just use 1.25 and 1.1. So for seismic, even baseline, we use slightly higher capacities because concrete gains strength over time. Steel is usually in North America, it's 10%, 15% stronger. So we don't use the basic design values. Our code says for your basic design, this one, use 25% extra on F'(C) and 10% on your rebar.
So this is not for the confining.
No, the confining effect is separate. This is just your basic materials. And then for overstrength, it says use 70% F'(C) and 30% Fy. So you run your run your moment curvatures based on those values. Okay. Sorry, let me just.
So we are applying these magnification factors on the actual stress strain curve.
No, you're applying that to the basic materials. So F'(C) is not 30, it's 1.25 times 30. Fy is not 400, it's 1.1 times 400, 440.
I mean, you are not applying on just the number you are inputting this like the material stress.
At the material level, yes, to the stress strain curve, not to the bending moment, because the bending moment is not going to, because one material is not the same as the other, right? So now when I look at the overstrength, then these are the values. So I go from say 4,600 at 12,000 to 5,200 at 12,000. So here is the model setup. I've got that model. These are my rigid links. These are my rigid links to model the areas of the joints. And these are my rigid sticks taking me all the way up to the CG of the superstructure. The first step I'm going to take is I'm going to apply my dead load. So I know what each one of the girder weighs. I put them up at the very top. Okay, because you have to start from a stress state. You can't just start to run a pushover when there is no bending, axial, shear, anything. So I'm loading my structure first with those values. Okay, that's the first step. And out come these dead load reactions. So this is just the axial load. So you can see my columns have, because the girders are symmetric, the columns get the same amount of axial load. This is the column dead load bending moment distribution. Okay. This is the cap beam bending moment distribution. You can see negative close to the column beam joints and then positive in the middle. What do I do now? I just go and I just set up a transverse load pattern. And I'm applying 100 kilonewtons at each one of those top points. Okay, so I've applied 400 kilonewtons of base shear. So if I just look at that, the seismic itself, just by itself, this is the bending moment pattern in my columns. Okay, so I've done the dead load, and this is the seismic. These are, both of them are linear elastic analyses, just static. This is what's happening in the cap beam. Okay, now I go and I say, I'm going to make a load combination. So in my next step, again, everything is linear elastic. I put all my dead load with a factor of 1, and I put my transverse load that I had defined, I put that with a factor of, I think this is 5.2. Okay, so here you have to just fudge this factor a little bit. So you can start with a 2 or a 3, and then see what your bending moments look like, and which section is getting close to its capacity, because you've got the P.Eng data aside that you can look at. So you can now output this to Excel, where you can have the demands and the capacities, right? It's all linear. So in a couple of tries with this factor, you'll get one section to hit its effective yield value. So once you've done that, you've figured out, oh, it's this top left that's going to form a hinge, and it's got a certain moment in it. So what you do is, you go in your software and you break that element there. So you basically have 2 joints at the same location with nothing in between. Okay, good. So you've generated the 2 points. We're going to insert a physical hinge here. How do we do that? So you break them into 2, and then you draw a 0 length element between them. And you can give a little bit of stiffness to that link, or you may just leave it as it is, but don't give it a very high stiffness. If it's starting to be as stiff as a column that's not hinged, then it's the same. You haven't done anything else, anything different. So you could give it a bit of a stiffness to model any post-elastic hinge stiffness. I would just, when you're doing it by hand, you can just leave it alone, because it's just going to be like 2% of the pre-hinge, and it's just not going to see anything. I've tried it, you barely see any increase. Now, you know that that point has locked in a certain moment, right? Where it formed the hinge, it had a certain moment. At that p-value that's there, the moment that it had was 4,700 kilonewtons. And that's what your P.Eng curve showed, that if whatever P it had, if it ever got to 4,700 kilonewton-meters, that now you're hitting your effective yield, so you're hinging. So what you have to do is, you've got to go and apply equal and opposite moment to the two ends, to each one of those joints, to lock that in. And sometimes, when the first time I did it, I saw my system go one way. Well, I had just applied them in the wrong sense. So if that ever happens, you just reverse their sense. And what you'll see is, once you've got it all correct, when you apply the same load with the broken system and equal and opposite moment locked in, you get exactly the same shears, exactly the same axial loads, exactly the same displacements. So now you know you've captured that state of equilibrium where the first hinge formed and locked that bending moment in there. Okay, now you do the same thing. You say, okay, that's my first dead load. That's the transverse one, the load pattern of 5.2. Now I'm going to add more to it. Okay, so this combination has more, the same, but I'm adding a different scale factor. And now I'm going to monitor other points. So now I make the first two as one combination, and then I go to the next one. I only need to put a 0.2 on the next one. And what happens is, I form another hinge. So you go through the second, and the second hinge forms. You do the same thing. You break it, you put an equal and opposite bending moment, you move forward. The third, the fourth. When the fourth is done, you know that you've got all hinges captured. And this is, this system went to, its hinging is like this. So the first one happens, hinge number 1, which is happening here at the top. Number 2 happens at the bottom. Number 3 happens at the trailing column bottom, and then 4 happens at the top. And here are the shears. Shear, 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 shear. So by this point, and at this delta, which is 56 mils, so you go from 41 to 43 to 44. So almost 2 hinges are happening pretty much simultaneously. 43 and 44 mils, there is no real difference. And when you run it in an automated fashion, they might happen at the same load step, because the program is probably not going to be that worried about the difference. So you form your first hinge at 2290 and your last hinge at 2490. So there is not a whole lot of increase happening in this system. It's going from 1 hinge to 4 hinges pretty quickly. And there is, starting from 40 mils to 56 mils, there's a good bit of increase from the first hinge to the last one. Now, when you're doing this by hand, you're done at this point. You can't do any more. Unless you put some stiffness in your link elements. Now, there is no stiffness there. If you keep pushing it, the program will just blow up because it has no stiffness at this point. You can't push it anymore. So what I wanted to bring to you was that it really is the gravity, just to sum it up, plus the seismic, and they're adding together and subtracting. One is being subtracted from the other, and you're getting to these points at these different locations at different times, at different force levels and different displacement levels where the hinges are occurring. And when you run, that's all it's doing. So every time a hinge forms, you go and you physically put a hinge there. But you have to lock that moment, so you got to apply the equal and opposite so that it cancels, but it's locked in there. And if you do it right, you run it again with the same parameters, and you will find that its deformed shape is exactly what you had before. Its displacement is going to be the same. The force effects are going to be very, very similar. That's how you know that you've got it right. And you can keep stepping through it and get to that point. So that's what a pushover is. It's an event-by-event analysis where you're capturing your nonlinearities as they're kicking in. Okay? So this is the Manders model. It basically works with the confinement. This is your original concrete. It fails over here, and that's this F prime C. But when you confine it nicely, it gets all this other energy inside that stress strain graph. This is where the first hoop or stirrup fractures. your ultimate strain is a lot higher and your ultimate stress is a lot higher. You can get anywhere from 3 to 5-fold increase in your crushing strain within the core as compared to the cover concrete. So this is just giving you the different formulas to come up with those values. Okay, so this is the last topic for the day. I think we'll cover this and then we'll call it a day. I have a couple of examples of the Manders model, then we'll go into the automated linear approach and how do we figure out if the software is giving us something appropriate or not. Then how do we run a pushover incorporating overstrength, and how do we utilize some of the plastic hinge? Yes?
Failure, the last one that we had there in one of the hinges happens before the other hinges yield. That's possible.
It could happen if it's badly detailed.
So if when we're checking in the software, after one yields,
yeah,
for all of the others, or for all of them should at the same time.
You have to monitor all 4 of them at the same time.
Yeah, but not only for yielding, for the
So that's very difficult when you do it by hand. Because now you have to come up with your rotations and divide it by the plastic hinge length to get your curvature, and then you got to go back into your moment curvature graph. When it happens on the through the automated thing, you have to monitor all 4 of them and make sure that something hasn't already gone past that point before something else has yielded. Now, what usually happens is if you've done detailing appropriately, it almost will never happen. But in order bridges, when you look at those, it's a very distinct possibility. Not as much of a possibility with new structures. Yes?
The PMs you wrote.
Yeah.
What?
This PM? Oh, the PMs, yes.
Yeah.
Yes.
Where do you get the P? Is it the P?
So the P is what you put in the software as the axial load on the column.
That's one P, but then
That's
the
1 P.
moment that-
And then the moment keeps increasing. So that's one moment curvature graph. And you have to generate many of them for a range of values of P. Yes. So that when you're doing this by hand, and as your axial load is increasing or decreasing, you're able to go back and see, now this is the P. Is my PM combination hitting that graph or not, that curve or not? The program will do it on its own. But when you're doing it by hand, you have to monitor. That's why I want to talk about these, because that's how these intelligent questions come out. Otherwise, people don't understand. Like, you would not have thought of it if I just said, okay, just put this in, let it run. Now you've been forced to think about it, right? So good on you. That's.
Sorry, Ken has one more.
Yeah, no, that's fine. I don't mind.
It's not a design one. Let's assume this one yields.
Mm-hmm.
So we put 2 moments
Mm-hmm.
here and put a link.
Mhm.
And the other one, so okay, let's move, and then this one fails.
Mhm.
So just remove the moment. It's just
Yeah.
the link there, right? Because
So if that one fails, as in it's exhausted its curvature ductility, either the rebar is ruptured or the concrete has crushed, you just stop right there. You don't go any further.
But I can go further. Right?
You can go further, but there is no reliability in the system at that point. So as engineers, because we're mandated with protecting public life, we don't want to take that risk of, oh yeah, this is already crushed. Yeah, it's probably going to be sitting there, but then along comes a little shake and then this thing just rips apart, right? So we don't want to go beyond that.
When you draw the moment curvature,
Mm-hmm.
did you consider it tension that will be taken by the concrete or only?
No, you can, but you can ignore that. So it depends on how you input the moment curvature curve in extract. You can give it a tension capacity, then it'll give you a little bit.
For the code, it says anything about it? Whether we should consider
I think the code is silent, but the practice is to just ignore that a little bit. tension in the concrete. Well, actually, sorry, I take that back, because when you look at this, you look at the moment curvatures, you see where the thing first cracks, right? That's up to then you're accounting for. So up to cracking, you account for tension in the concrete. But once it cracks, you assume that the cracks cannot. Once it's cracked, it's just gone. So remember the first line is up here, and then it flattens out.
So this means considering this because in your tension, if it is stress is less than that one, so you consider that much tension.
Well, if you're going to be, your design is going to be so, like if your demand is so low that you're not even cracking the concrete, then you probably don't need to run any kind of, seismic analysis. You're not hitting it with any kind of real force. Okay, so let's see how we can do on this. So I'm just going to quickly run through the Matters model confined concrete. I want to focus a little bit on pushover using the automated nonlinear approach and obtaining some software output, making sure it's adequate, because I've run into some issues before. How do we run the pushover by incorporating overstrength and then maybe plastic hinge length and output utilization? We'll see how we go about it, and if it's getting late, we'll defer it to tomorrow because we have some time tomorrow. Okay, so you can run through this. Basically, your F prime C is 35, your hoop yield is 400 MPAs, and your steel ultimate strain is 0.09. The column diameter is 1525. Clear cover is 70, and the spiral is 20 Ms at 100. So now we want to come up with the F prime double C, which is the confined concrete, and the the epsilon double C, which is the confined concrete strain value, the ultimate ECU. So the spiral rebar ratio is given by 4 times the area of spiral divided by the core dimension, the diameter of the core multiplied by the spiral pitch. So it's 4 times the 15 M or 20 M is 300, and D prime you can calculate by subtracting your 2 times your cover, and it's to the center of your hoop. So then you go 2 times 20 over 2, so you get your D prime. So your transverse reinforcement ratio is 0.0088 basically. The confining stress that it provides is 0.5 times that, and that gives you 1.76 MPAs of confining pressure on your concrete. And what we do is we assume some inefficiency in that, so we only use 95% of that. That's what Priestley or I think Mander has come up with. So instead of 1.76, we use 1.67. And then to come up with your F prime double C, you have this factor that you need to multiply with the effective F prime C, which is 25% on top of your basic. So your basic was, I think, 30 or 35. 35 times 1.25 is 43.75. That's your base strength. That's your cover concrete strength. And then F prime del is in there, F prime CE is there. So you calculate that and you see you're getting about 25% increase on top of that. So you end up as the core concrete having a strength of 55 MPAs. And then you look at this, this is the strain values. You see there is a minimum of 0.004, and this factor accounts for all the extra that you get from confining. And that's about double. There's a factor of 2 on the basic, so you end up at about 0.012. Steel pile. Here the rho S is 4 times the thickness of the pile divided by the D, which is the diameter, so you can come up with that, 7.63, so you can see that's a lot bigger. 0.95 of that is 7.25, and you run through the same thing, and now you have a factor of 85% instead of 25%, and a factor of 4 instead of 2. So a steel, which is a shell, which is constantly confining it everywhere, is giving us 4 times on the basics. You end up at 0.02, and instead of 55, we're up at 85 MPAs. So how do we run this automated nonlinear analysis? We do the same thing as before. We make the model. We have the dead load applied in the one pattern, same thing. Then we have transverse 1, and its self-weight is 0 because this is not a dead load case. Okay, now this is SAP, and I think, or CSI Bridge and other softwares are kind of similar. When you're running a nonlinear pushover analysis or any kind of nonlinear analysis and you're starting it from a stress state, it wants you to run the original analysis and nonlinear analysis too. Otherwise, it just doesn't let you do that. It doesn't make any difference, but that's how it's written, I think. So if you were to have this as linear static, it wouldn't let you set that as nonlinear static. So you have the dead, and then you have the pushover. Those are your two load cases that you define. So in this, I've applied the vertical loads. That's my dead load case. And my scale factor is 1. And the dead all obviously starts from 0 initial conditions. So you have nothing, and then you apply the dead load. Okay? And I'm not interested in intermediate states. I just want to know where the stress state is right at the end of the dead load. Like, I don't want to apply it in 10% increments or anything. So I just say, give me the last one. No P delta or nonlinear effects. Just give me straight up first order analysis. Now I have to define a load pattern for it to carry out the pushover. So this is really saying push the structure in this, replicating this mode shape. And bridges with this type of bend, they're really just going to behave, this bend is going to behave in the first mode. It's not going to be behaving like that. So I just apply unit loads at the very top, and I say that's my transverse pattern. So the program understands that these are not actual loads. This is just telling it, look, it's a uniform push in one direction. If I put ones here and then I went down and put 0.6 over there going the other way, then I probably would be modeling the second one. And it was just going to push it like that. It's going to keep pulling on it here and keep pushing on it there. But on a short bend, that's not going to happen, right? So we know it's going to act in the first mode shape. This is just defining it for the program. And it's going to do its work. This is different now. I start from end of the nonlinear case dead all. I don't want to start the pushover from an unstressed state. So I'm telling it, look, this is a nonlinear case, just like the previous one was, but the previous one was starting from 0 initial conditions. There was nothing on it before the dead load was applied. For the pushover now, the dead load is already applied. I say this is a load pattern, which I defined as transverse 1. I have a scale factor of 1. I say this is displacement controlled. So I'm going to tell you how far to push in terms of displacement. This is not force controlled. I'm not going to tell the program apply 1500 kilonewtons of load because it might firm the mechanism at 300 kilonewtons. I just don't know. So why would I use a force controlled analysis in this case? I'm only going to use a displacement controlled analysis and let the program come up with the corresponding forces. I don't want just the final number. I want multiple states because I want to be able to look at that whole graph. I want to see when the hinge forms in the first location. When does it inform in the second, the third, the fourth? So all of that I'm setting up. I'm saying take my joint 37, which is, I think, one at the top, at the middle of the cab beam. That's joint 37. Take its U2 degree of freedom, which is transverse, and push it by 0.1 meters. So push it 100 mils and tell me what happens as you push it all the way to 100 mils. And I'm saying, I don't know what this conjugate displacement is. I've never been able to make it work. I always say use monitor displacement. So monitor the displacement at that joint, keep pushing it, and then tell me what's going on as you're pushing.
So what was the purpose of applying the unit loads in the previous?
That's just, I was saying, that's just telling the program what mode shape to model. So
That's
when I
for
put
the mode
1, 1, 1, 1, that just means it's going to go in the first mode at the top. So this is going 0.1 meters with that mode shape in mind. So if I had pushed it like this, if I had said, let's do it this way. Now it's going to push it and it's going to look like this. You're bent as it's being pushed. That's the mode. That's the second mode it's going to model. And
100 on the top and 16 in the middle.
These are just, again, these are just telling it what ratios these
So
are.
this 0.1 will get multiplied with that.
Yes, exactly. No, it will push it. So I'm saying you monitor this point in this direction until this displacement is 0.1 meters. So it would keep pushing it in this way until this moves 0.1 meters over. But now it's not going to look like this, which is what it should. It's going to look like it's following the second mode shape.
So this is kind of 3 loads we have applied on this bend.
This is not a load. This is not a load application. This is just telling it to push it in this direction just uniformly. It's just a pattern. So it's just saying this is a unit load. I could put 300 here. It doesn't mean anything for it. So it just works with this value, and it takes this as the load pattern.
Fine. So how you planned that actually? Have you got it from the model analysis and you selected a
No,
model?
but I just know that if you have a structure like this, which is what the bent is,
Okay.
under all circumstances, it's going to behave like this, which is its first mode. Because this is, if this were a tall building, you could probably see that happening.
Yes. Okay.
If this were a 2-story bent, you could possibly see it going this way, and you could possibly see it doing that. So one moving this way, 1 story moving this way.
So you will.
But that's not going to happen, right? Because this is a single bay. It's like a single-story short building. It's going to go in the first mode.
But if it would have been a double-story one,
Then I would have had to run 2 pushovers, one in the first mode, one in the second mode. Then I would have. That's what we call a modal pushover, and that's quite a bit more involved. And my thing is, if you're ever going to run a modal pushover, you're better off running a nonlinear time history. Just run your pushover in your first mode, understand how the load is flowing, but beyond that, just go to a nonlinear time history. There are people that are doing modal pushovers. I don't buy into that philosophy a lot more because you get to the same point where the modes are not happening at the same point, and then you're bringing in the CQCs and SRSs, and it becomes a long, drawn-out process. Well, if you're going to put in that much energy into your analysis, you might as well run a nonlinear time history. That's just my personal take on it. Yes?
So if the links that are rigid, you don't have to put 3, 1 loads, right?
No, you can just put 1. It's just that if you put the 1 only, and you have 3 girders, remember each girder is going to put a shear force into the cap beam, right? Each girder is trying to move, and its tributary mass is where the load is getting into the system. If you just put the one in the middle, everything to the right of your cap beam is going to go into compression. Everything here is going to go into tension. No, it's you'll see the compression here and the tension here. That's not going to change, right?
Yeah.
So it goes just from pure statics. So you don't want to get incorrect axial loads in your cap beam. Whereas if you do this, now you're capturing the appropriate. Maybe it's 1 and 0.8 and 0.8 if these girders, outer girders, are a little bit lighter. But 111 is kind of giving you a pretty uniform. This is how you're moving. So it's just the pattern there.
so why it's not in the units of displacement rather force?
Because this is just giving you, this is just telling the program that's how they've set it up in CSI Bridge. Another program could say give me displacement.
So it's just a vector.
It's just a vector. That's exactly it. It's just a vector to define how to push it. That's all. This is where the control happens, and it says in that vector sense, push that point all the way to 100 mils, this joint in this degree of freedom. Okay, so that's what I'm monitoring. Assuming that my cap is pretty rigid and that this displacement and this displacement are going to be very, very similar. Now I say, look, I want multiple states and I want a maximum safe states like 100 states. So if I'm moving 100 mils, I'm pretty much capturing the state at every mil. That's overkill, but that's for demonstration. I've said, okay, well, just do it. This is pretty standard. I mean, you can play with the convergence tolerance and et cetera, et cetera. If it's not converging, you can increase this. You can increase the convergent tolerance. You can increase the maximum iterations within each step. That's your standard nonlinear stuff that you can do. Then we go and we define the hinge properties, because remember, we haven't assigned any hinges to it yet, right? It doesn't know there are any hinges. So we go to hinge properties, we give it a name. Our hinges are interacting hinges. They're not just moment hinges. So there isn't just one moment, one plastic hinge in moment. There are multiple values. For each p-value, there is a different m value. So I say to the program, use an interacting p-m2 value. I'm going to give you 11 axial forces and 11 bending moments. And then, so these are the axial forces that I want to give the program. So I'm giving it this PME curve, the PM nominal effective curve, because that's how it knows when to introduce a hinge. When it goes in there and it finds that you've hit a certain point on this surface, it goes and introduces the hinge on its own now because it's automated. I've given that away from myself. I've given it to the program. That's the user interaction surface. When you click on that, now you have the P's, and you will have done your moment curvature analysis, and you will have calculated the M, so you put those in here. For each of the P's that you put in earlier, this just showed up. It doesn't converge if you have any dimples in the curve, so it's got to be a convex surface. That's a bit of an issue, because if it does this, when it's running Newton-Raphson or whatever, it's going to have issues, converging in this zone. So if your PM graph looks funny, so maybe this was 3,000 and had to fudge it to 2960. If it's changing it by 2-3%, I would just leave it alone. Okay, so you've defined the hinges. This is what post-elastic stiffness you want to give it, if you want to give it any. So your rear moment is 1% higher. I haven't really given it anything. I've just said it's flat once it forms a hinge. You select the column, the section where you're going to assign the hinge, you select it, and then you go assign hinges. This is just all project or specific to the software. You take that hinge and you assign it with a relative distance. It depends on how the member has been drawn. If the member's been drawn this way, this is 0 and this is 1. And I want to assign the hinge right here, so I've said relative distance is 1. If it were drawn top down, this would be 0, this would be 1, I would assign it to 0. That's just software specific stuff. So you got these hinges, you assign it, now it shows you that you've assigned the hinge. So you can do that on all 4 locations. If it's a new design and you know that's where hinges are going to form. If it's an old design, you might want to assign hinges to the cap beams here and here. And maybe if you're finding a lot of curtailment of rebar, all of a sudden drops, you might want to also put one there just to see if it, instead of forming it here, it forms right there. Okay? Yeah. Say that again. Yes, I am, because I have understood the structural performance enough, and I'm the designer. I'm going to make sure that I have my columns, the maximum demands occur at the top and the bottom. So yes, I am dictating to it that that's where they're going to form. Yes.
And you're assuming that they are like at the distance, like using that's the equation for the plastic hinge.
Yeah, so that will come in a little bit. Yes. So this is a lumped plastic hinge, so it's just at the point. This is lumped plasticity. For those of you who are familiar with fiber models, you don't need to define it because fibers just pick it up on their own. It just fiber hinge forms as it forms. Okay, so the top two and the bottom two. So you can see all four have been assigned now. So now then I can run it, right? And I say, well, push over step number 5. It shows that my first hinge is formed. My displacement is 39 or 40 mils. Yes?
Yeah, you don't need to define a moment curvature.
No, I don't. I'll tell you what to do with it separately. Yeah, because in a lumped plasticity model, you need to know it for figuring out the n number, but you don't need to put it into the program. From the moment curvature, you do need to know the n nominal expected to put the P.Eng graph in there. Okay, and then we'll do something with it to move it forward. Okay, so that's the first hinge that formed at about 39. The bottom one forms at about 43. The next one forms at about 44, so pretty much the same. And the last one forms at 54. So now you see all of it as it's formed. So how can I tell that I've got something correct? Well, when the first hinge forms, I know what step that is. Or say this is another one which is forming at step 19, for example. I go in there and I read the axial load, and it's about 10,000. Okay, so I know, okay, when the hinge is forming, it's 10,000, and believe me, I've been bitten before, and the bending moment is 4,500. So for a P of 10,000, the bending moment is about 4,500, and that's when the program has decided to put the hinge there. Well, guess what I can do? I can go into my PM table that I've given to it and see if they're close enough. And if they're not, then something is wrong, something is going on. So you always want to go and have a look at your input and make sure that it's forming a hinge when it's pretty close to your input. Otherwise, something funny is happening. So one of the stranger things that I've had, so you see at minus 10,000, it's about 4,700. So that's very, very close. It's picking the number pretty accurately. Back in the day, what I did was, instead of putting these 2,000 meter or 2,000 kilometer intervals, I said, oh, this is too crude. I went to 100 kilometers, and I had a big table. And I started to get garbage out of SAP at the time I was using. And to this day, I don't know, but whenever I've tried that, it just goes bonkers. So sometimes trying to be too smart actually bite you. And that's why I'm saying, don't trust these things. Because to me, if I was giving it points that are rather close, it should be able to converge better. And it wasn't giving me any error messages. It wasn't saying you have a dimple and I can't converge. It was converging. It was giving me numbers, except for when I went and looked at the P.Eng for a given hinge formation, it was way off. And as soon as I went back to 1,000 or 2,000 kilonewton gap between my points, it started to function just fine. And that's why I'm saying you always need to go back and check. Whatever software you're using, do these engineering checks. Don't forget them. They can create problems. So this one, an axial load of minus 5,000, I think. A bending moment of minus 41. You can do that. And then this is going to show you your static pushover curve. So this is showing you the whole curve. This is all the way to 0.1 mils, where you can see it's 100 times 10 to the minus 3. This is where the 3 or 4 hinges are forming within about, 10 mils or so of each other. So sometimes you'll go there and you'll see your pushover curve is doing something really, really funky. And right away you know, look, my stiffness should be changing gradually. It should not be coming back up, or it should not be doing something that doesn't physically make sense. You need to check for those things. So these are the hinges. We can see some hinge results. So this is a particular hinge. And I can see when it forms, you see there are no plastic rotations in it. It's just formed at the step number 20. And its backbone curve looks like this. It's a rigid plastic hinge because any elastic deformation happens prior to the hinge forming. So the hinge just works with this. So it's just hit its plastic point here. So this vertical line is not shown. And it's on the negative side, negative bending. So it's just formed. You see there is no, again, if this is forming and you're seeing a pretty large plastic rotation value, you know that that's not right. Okay, M2, same thing, R2 of 0. Now here, you see that this is at 22, it's gone past, there's a plastic rotation, and you see now it's starting to travel along this plastic path. Same thing, a different one, more plastic rotation. This one is just forming there, and we basically go through this. This is a different one, so this is another pushover. Oh, so okay, so this is the overstrength pushover. And you will see that the overstrength base shear is 2700. The other one was about 2400. So overall there is about 300-400 kilonewton of base shear increase. The bending moments are obviously going to be larger, and the shear forces in the columns are going to be larger. Okay, so here now you see this is getting all the way up to 5,000. And so now you want to design your cap beams and your column shears and all that corresponding to these overstrength demands. Okay, so when you're looking at displacements and curvatures and ductilities and strains, you want to stick with your basic nominal expected. When you want to get shears in your columns, shears and bending moments in your cap beam, joint shears, foundation forces, you want to be running the pushover with the higher capacities so you get higher demands going into those elements. Okay, so these are column top moments for the overstrength demands, bottom axial. This is what you would use for your foundation demands. They're much higher than the basic 4,000. They're up to like 5,300. So there's a good 20% increase. You need to be designing your column foundation joints and foundations or whatever for these higher demands. Also designed for these shear values, accounting for the degradation in the plastic hinge zone. So you're gonna do that. I think this is where we'll stop, and we'll pick it up tomorrow here. I'll have a little bit of an overview of just, this will give us an idea of how to just come up with a one-step pushover to get your, this is a pushover by hand, and you'll see how close it gets to the other two methodologies that we've got. So when you run a pushover, you can do something by hand pretty quickly in, what, 3-4 pages, like 3 pages that get you up to, you know, within 3% of this. Sorry, so this is iteration number 3, and I'll explain it tomorrow. This is 3% of iteration number 2, so I'm saying I've converged. But the difference between this and the SAP automated value is 5%. So do a check on SAP or whatever software you're using. Don't just blindly follow it and accept it. Because with some very simple hand numbers, which I'll explain tomorrow, you can get to the ballpark. And yes, when it comes to these strains and all those values, you can rely on the software, but now you have some comfort that it's giving you something needed. Okay? Thank you very much.
Thank you.
So tomorrow we are going to start at 9?
Yeah, 9 is fine, and I think it'll be 5 hours or so, if that's okay. Yeah.
Yes.
Yeah, about
So-
1 or 2 we can
Yeah.
do. Yeah.
2.
Yeah.